Please let me know if you can see it. Thank you, Sean. Thank you, Aidan. Okay, now before I'm starting, this lecture, I want to make a small announcement about this lecture. It will be, just a bit shorter, and the lectures or the notes for the op-amps, the operational amplifiers, are already posted on D12. That's why will be based on all the notes that are on D12, and in the same time we have to do the SPL, the student perception learning for this course. That's why I will not finish the unit 8 or the second portion of of this topic. I will do just the first part, and I will give you some extra minutes or extra time to finish or to complete the SPL. In the same time, I will give you the instructions how to log on and do the SPL at the end of today's lecture. Now, going back to what we discussed our previous lecture, we discussed about the op-amps, the 3 stages for the operational amplifier. That's the internal design. But we are not using, a lot of the internal design. Most of the time we are using an external device, or 2, 3 external devices or external components that may be used and to determine or to have a precise gain. Usually there are 2 resistors, or a resistor, a diode, or a diode or a resistor and a capacitor that will make the negative feedback circuit. We can look for a negative feedback circuit as a group or a set of external devices that can be adjusted, that can be moved around the op-amp, that will do different functions and different circuits that may be used to with an op-amp to have different applications. Now, to remind you about the op-amps that has an external feedback network or feedback circuit, those are the advantages of an external or a negative feedback for the op-amps. We have a precise control gain. Remember that the theoretical or the gain for an open circuit, or the gain that is given, it's provided by the manufacturer, it's about 200, or in this range. We are using the open gain or the AOL, again without having any external circuits, any external devices or circuits between the input and the output. What a network or a feedback network does, it will return, or actually it will apply a portion of the output voltage to one of the 2 inputs of the op-amps. Another advantage for using a negative feedback is increasing the bandwidth, the increase in the input impedance, and reduce or decreasing the output impedance. Remember that we have the AOL, open circuit gain that is provided by the manufacturer. Once we are using a feedback, a network or a negative feedback for an op-amp, the gain becomes a closed loop. The closed loop, again, is the connection between the output and the input. That's why it's called the closed loop gain for an op-amp. Notation is the ACL, and the A, I mentioned that it's for the gain or the amplification. CL is the closed loop. Means that we are dealing with two gains, the open loop or the AOL gain and the closed loop gain. Closed loop gain has the external devices or the external components attached between the input and the output. And we'll talk about, some of these advantages. That's why I produce, those advantages because we'll do, some calculations next week and in-class examples, how to determine the gain, how we can increase the bandwidth, reduce impedance, and the increase in input impedance for the op-amp. I mentioned that, one of the advantages is increasing the bandwidth. Now, we are looking, in the advantages of the op-amp and increasing the bandwidth. I mentioned that the bandwidth or the frequency of the op-amp is pretty large, but there is a limitation on how we are using or what gain we are using for a certain circuit that it will limit the bandwidth. Suppose that we need a constant gain for a circuit that it's using or it's applied, let's say, 100 or 1,000 hertz. You notice that from this curve, and the characteristic of the op-amp for a closed loop circuit or an open loop circuit has a decay in 20 dBs per decade, and you notice that it's a pretty constant decreasing the amplification or the gain as the frequency increased. By simply, using the external resistors, for example, or external devices, we are decreasing the gain. You notice that there is another notation for gain as the uppercase G. Now, in order to make, to stay consistent, I'm showing, some other notations, but in the same time, I will stay closer to the notation that it's used in the textbook. And that's why I will stay with the notation that we already mentioned is the gain for a closed loop, not the G. But just to show you that it's quite possible to see another notation for the gain. Suppose that I'm using, the op-amp for an input frequency of, 1 kilohertz or 1,000 hertz. You notice that the maximum gain that can be used for 1,000 hertz, it's about 1,000. But if I will lower the gain by 10, means that if the gain becomes 100, you notice that the projection of the drop by 3 dBs is about 10 kilohertz. Means that if the gain is decreasing, I can have a larger bandwidth for the amplification for the gain in applications. Means that as a suggestion, you may use the op-amps in your capstone project or any other projects. I'm suggesting to use a lower gain to have a wider bandwidth. Means that the maximum bandwidth I mentioned that is just a bit above 1 megahertz, But for 1 megahertz, I don't have, too much gain. It means that I'm using, or I can use, two cascade amplifiers with a lower gain to have a larger bandwidth, and the product between the gain and the bandwidth is almost constant. Again, we can make, this approximation that, the product between the gain and the bandwidth is almost constant because we have, the almost, a constant decrease or a constant decay of the gain as the frequency is increased. One advantage again of lowering the gain, and I mentioned that not too many or not in many applications or not too many applications are using the open loop gain, which is 10 to power 4, 10 to power 6, or 10 to power 5 of the open loop gain. That's why most of the time we are in this range, between 5, 10, 100, 1,000. If we are going on higher a higher gain, the bandwidth is limited. Means that always take into account what is the bandwidth that is required to amplify a signal. Now that's one of the topic that I will come back and tomorrow, and we'll discuss a few more details, but basically it's the same approach. Always the product between the gain and the bandwidth stays constant. On the second unit or the second topic, we'll discuss about the two major or basic circuits. We'll talk about the inverting amplifier and non-inverting amplifier. In calculations, we have to make some new notations, and one of them we are already familiar with it is the gain. I mentioned that most of the time we are using A as the gain, but in the same time we are using B as the attenuation. I mentioned that A, it's most of the time used for amplification, or when the output voltage is greater than the input voltage, and B is the attenuation. The attenuation of a signal when the output voltage is less than the input voltage. That's why using those two symbols, A for the gain and B for attenuation, or A for amplification and B for attenuation. We mentioned that we are using a negative feedback or some external components. We can reduce the gain to an equation that has the gain for an open circuit over the 1 plus the gain of an open circuit or open loop multiplied by the attenuation of the op-amp. Again, that's the A or the gain for an open loop. Now we can simplify the design. Actually, we can determine, we can control the external components much easier without knowing any details about the internal design of an op-amp. By simply changing the components, the external components that may be added around the op-amp, we can alter, we can define a different function for the op-amp application. That's why I include here the feedback also allows us to alter the circuit characteristics, and we'll talk about by the end of these lectures about the or this topic, the op-amps or the applications of the op-amps as the integrator or differentiator. The ACL, the closed loop gain, that's the notation that I'm using from now on to find what is the gain of an op-amp with an external feedback circuit or an external feedback network. Now, if a portion or a fraction of the output voltage is returned to the negative or the inverting input, you notice that in this diagram, let's try to use the tools in this diagram. A portion of the output voltage is returned to the inverting input or the negative input, which is called the inverting input. Now, using two external resistors, sometimes you will see the R1, R2. In your textbooks, and your textbook are using the RF and RI, and in my opinion is very simple to identify the two resistors. RF is the feedback resistance and RI is like the input resistance. That's why in lab I'm using, or I'm trying to use the same notation as the RF and the RI, but in the same time we can see we can use the R1, R2 or any other notations for the two resistors. You notice that the way that it's connected to the output of the op-amp. You notice that the RF is series with RI. Means that works as a voltage divider on the output voltage. Means that the V out, or a portion, a fraction of the output voltage, is returned or it's fed back into the inverting input. If the two resistors works as a voltage divider, means that we can precisely define or find what is the VF or the feedback voltage. The VF is for the feedback because comes from the feedback circuit. That's why the VF representing a portion, a fraction, or a precise value of the output voltage that is returned to the inverting input. On the positive input, on the non-inverting input, it's applied the useful signal. Suppose that that's an AC input signal applied to the non-inverting input. If the circuit has, this configuration, it's called the non-inverting amplifier. Again, non-inverting amplifier is in terms of the phase shift between the output voltage and the input voltage. If the two voltages are in phase, means that the phase of the output voltage is or has, the same phase with the input voltage. They are calling, in phase voltages, means that the op-amp into it will amplify the input signal without changing, without shifting the phase shift between the output and the input voltage. Now, the abbreviation, you may see, most of the time, and I'm putting, in brackets, the non-inverting, the NI, because we may have, the same characteristics or the same gain for a non-inverting or for an inverting amplifier. To make the difference between the two, I'm using, this notation, which is very simple, to use, using, or having the NI in brackets, means that for a non-inverting amplifier. Now, if I'm looking to calculate what is the returning voltage or the VF, the RF series with RI, I can use the voltage divider's rule to determine what is the voltage returned to the inverting input. And if you remember, is the resistance in question, because the Ri is connected to the ground, divided by the total resistance of the circuit. total resistance of the circuit is the Ri series with the RF, or the Ri plus the RF multiplied by the V out. Means that an easy way to determine the VF, or the feedback voltage that is returned to the inverting input, is the equation, the Ri over the Ri plus RF. Again, from what is coming, that's a series type circuit, and that's the voltage dividers rule for a series type circuit. Now, remember what an op-amp does. It will amplify the difference, or amplifies the difference between the two input signals. Means that the V plus minus the V minus, means that the voltage applied to the non-inverting input minus or subtracting the voltage that is applied to the inverting input. Remember, we define the differential amplifiers, or the V-diff, that's the differential voltage, which is the difference between the two inputs, the non-inverting input and the inverting input. Now, making some calculations, we can determine that the output voltage of the op-amp using a negative feedback is the input voltage multiplied by the gain of the circuit. But that's the gain of a circuit, which is the open loop gain, amplifies the differential voltage, or the voltage between the two inputs, as the Vin minus the Vf. Remember that we discussed about B as the feedback attenuation. Now, the feedback attenuation, or how we can calculate the portion, or the fraction of the output voltage. You notice that if I'm grouping, the two resistors, or the RF and the Ri, it will limit, or it will reduce the voltage that is applied to the inverting input. Means that the ratio between the Ri and the sum of the two resistances, it will represent actually the attenuation factor, or the feedback attenuation of the feedback network. Now, having those two equations, or those two new equations established, we can determine that the gain for a closed loop circuit for a non-inverting amplifier. You notice that again the Vin is applied to the non-inverting input, means that the output voltage is in phase with the input voltage, and the gain of the non-inverting circuit is equal with 1 plus the RF over Ri. Now we can discuss about this equation, and we'll have a special case of a non-inverting amplifier. An example of a non-inverting amplifier. Suppose that RF is 82, the Ri is 3.3, 1 plus 82 plus divided by 3.3, it makes 25.8. You notice that I can have a precise gain if I'm using precise resistors. Let's say 2%, 1%. That's why I use precise resistors in lab. We can determine a precise gain for a closed loop circuit. Again, that's the gain for a closed loop for a non-inverting amplifier, which is defined as 1 plus the RF over Ri. You notice that the gain is always a dimensionless number. Sometimes it's larger or smaller based on the two resistances. It means that without knowing the basic or the internal design or the internal components of an op-amp, we can preset, we can define a precise value for the gain of the circuit by simply adjusting the two external components, the RF or the RI or both of them, to have a precise gain. Now, a particular case of this circuit is called the voltage follower. Okay, what is a voltage follower? I'm looking now in this equation here. You notice that the gain for a closed loop circuit, for a non-inverting amplifier, I'm having, the ratio of the two resistances, RF over RI. Suppose that I'm making the RF as 0, which is actually replaced with a short circuit, and the RI as an infinite, means that I'm replacing the RF, which is, the resistance that it's connected to the output of the op amp, with a short circuit. I'm making the RF as 0, which is, replaced with a short circuit, and the RI, or the value of RI as an infinite ohmic value, which is represented by an open circuit. You notice that the output voltage is actually returned to one of the two input voltages, and the circuit becomes a voltage follower, and the abbreviation for a voltage follower is the VF. If for a non-inverting amplifier is the NI, having the two values, or the two new values for the RF and the RI, the circuit becomes a voltage follower. You notice that in this equation, if I'm replacing the RF with 0 and the RI with infinite, I'm having, just, the value of 1. 0 divided by infinite is 0. And in this equation, the gain for a closed loop, non-inverting, with the two values, or the two new values for the equation, the gain becomes 1. Means that the attenuation, or B, is equal to 1, which makes an open or a closed loop gain of 1. A voltage follower. Now let's look, for some applications and what are the advantages. If I'm looking back to any of these equations in terms of the gain, there is actually no gain or unity gain. Means that the output voltage, it's the same with the input voltage. There is no gain. But what are the advantages? In terms of the input impedance, suppose that I'm applying a signal that requires a very high impedance for a circuit, but on the output I'm using a transformer, for example, which has a very low impedance. You notice that without having, any gain, the voltage follower can be used as an impedance adapter. I'm adapting, a very high impedance that is required by the Vin with a very low impedance that is required by the load of the circuit. Means that this circuit does not have any gain, but in the same time, one of the advantage, or applications, for this circuit is as an impedance adapter. Means that a very high input impedance and very low output impedance, it's the most important property or characteristic of a voltage follower. Now we can look, for the loading effect. The loading effect in terms of the input voltage, or the loading effect in terms of the load that is connected between the output and the ground of the circuit. And I put, an example, the impedance of a transformer. Usually the impedance of a transformer is very low. Now I cannot connect, the an input signal or input voltage or an input source for a voltage that requires a very high impedance to a very low impedance. Remember that Maxwell theorem, always, the best or the highest transfer of power is when the load resistance is the same with the internal resistance of the voltage source. That's why we may use, this circuit as an isolating circuit between the input and the output. Again, we can look, for two separate circuits. I'm not having, any gains. The voltages are in phase, and we have the two different requirements in terms of the input impedance and the output impedance for this circuit. Now, in terms of the input and the output impedances for the non-inverting amplifiers. Now, the two notations that it's used, that the Zin that is given is provided by a manufacturer without having any external devices or any external or a feedback circuit connected between the output and the input. That's, provided by the manufacturer. The Zin for a non-inverting amplifier is greater than the input impedance given or provided by the manufacturer. And you notice that it's 1 plus the gain for an open loop. Again, that's, provided by the manufacturer multiplied by the B. B is the attenuation, and you notice that, again, B is defined as the Ri over the two resistances, Ri plus the Rf, multiplied by a large gain, and is 1 plus, this number means that the Zin for a non-inverting amplifier will be greater than the Zin. We can assume it's a very large value. Yes, we'll make, some calculations to determine what is the input impedance for a non-inverting amplifier with a predefined RF and RI, and you will see a very large input impedance when the feedback resistor or feedback network it's connected between the input and the output. On the output output impedance for a non-inverting amplifier, you notice that is the provided Z out over the 1 plus the same bracket, 1 plus the gain for an open loop, that's again provided. B is defined by the two resistances, Ri and the Rf. You notice that the Z out, or the impedance that is provided by the manufacturer, is divided by this bracket, and this bracket is greater than 1. It's 1 plus the product between the gain for an open loop multiplied by the attenuation of the circuit. Means that the bracket is greater than 1, means that the Z out, or the initial impedance of the op amp, is divided by a number that is greater than 1, which will reduce the output impedance for a non-inverting amplifier. Just to give you some ideas, ahead of time, the Zin, I said that it's in term or in range of mega ohms, tens per 100 mega ohms. On we'll do some calculations, you'll end up with, or will end up with a very large values, like hundreds of mega ohms for a non-inverting amplifier, or few giga ohms, depending on the RF and the RI, or depending on the attenuation of the circuit. In the same way, I can give you some ideas about, the Z out. I mentioned that the Z out, usually it's around, 100 ohms, I would say that. If it's connected in a feedback network or as a non-inverting amplifier, the Z out becomes probably, less than 1 ohm. It can be anywhere, 0.05, 0.5, 0.001, and so on. Means that it will reduce the Z out, or the output impedance of an op amp, or it will increase the impedance for the non-inverting amplifier. I mentioned that, again, the Z-in for a non-inverting amplifier, it's much higher than the Z-in that is provided by the manufacturer, and in the same way, looking, for the other impedance, the Z-out, for a non-inverting amplifier, it's much smaller than the Z-out that is provided by a manufacturer. The voltage follower, if we are making, the B equals 1, again, we know from what is coming, B equals 1, making the Ri as infinite and the Rf as 0, we'll end up with almost, the same equation, except that instead of having, B, it's having, I'm replacing B with 1. And based on, the same two equations, again, I will remove the B, or I'll replace B with 1 for the Z out, and I'll do the same thing on the Z in, and I will end up with, the other two equations that are applied for a voltage follower. A voltage follower has, or one of the best, or one of the highest input impedances and the lowest output impedance for the op amps. That's, due to the value of the Ri and the Rf. And we mentioned that, the output impedance is very high, or much higher than the regular non-inverting amplifier, and the output impedance is much lower than the output impedance for a non-inverting amplifier. Now, I will stop it here, and I will continue tomorrow with the inverting amplifier, and I'll give you, the access on the D12, just to give you an idea, and we can use,